When you write a line of code like this in C++, what's the mental model in your head? Most people would say, jump over there, execute the function, push a stack frame, come back. That sounds about right, doesn't it? But if I asked you, what specific steps does the CPU take? Which registers change? What happens to the memory? Why does a function call have a performance cost? Many people wouldn't be able to explain it clearly. In today's video, we start with the most ordinary line of code for a function call and dig all the way down to the hardware level. You'll discover that a function call isn't as simple as just taking a jump. It's a miniature state switch. Let's look at a very simple piece of code first. Just an add function called from main function. Seems simple, right? But from C++ code to CPU execution, the program doesn't just mysteriously jump in. First, the compiler performs syntax analysis, generates intermediate code, then generates assembly instructions for the target platform. And finally, the CPU executes the assembly instructions one by one. On x86 to 64 platforms, a common calling convention is the first few integer parameters are passed through registers, like RDI, RSI, RDX, RCX, etc. So before the call, the compiler generates instructions similar to these. The key is this instruction, call add. It's the soul of the entire function call. So what does this instruction actually do? First, it's important to understand that call is not simply a jump. Call performs two atomic operations in one go. First, it automatically pushes the address of the next instruction onto the stack. This address is called the return address. Second, it jumps to the first instruction of the TAD function. In other words, every function call leaves a roadmap back on the stack. But the JMP instruction you usually use only jumps. It doesn't push anything onto the stack. That's why if you jump with JMP, you can never return to the original position. The reason a function can come back after being called is entirely because call planted that return marker for you. This detail is crucial because from this moment on, the stack gets involved. When the CPU jumps to the add entry point, it doesn't start calculating the addition immediately. It first needs to set up a stack frame. What is a stack frame? You can think of it as a function's dedicated temporary workspace. Every time a function is called, a new stack frame is created. When the function returns, that stack frame is destroyed. A typical stack frame prologue looks like this. Let's explain. The push instruction saves the previous function's stack base pointer, RBP, onto the stack. The move instruction assigns the current stack pointer, RSP, to RBP. From now on, RBP becomes the anchor point for the stack frame. Subsequent access to parameters and local variables will be based on RBP. The sub instruction moves down 16 bytes from the current stack top. This step reserves space for local variables. Once these three lines execute, a complete stack frame is established. A standard stack frame typically contains these items: the return address pushed by call instruction, the caller's RBP, the function's local variables, and registers that the called function must preserve. Now, do you understand why recursion can cause a stack overflow? Because with each call, the stack space extends downward. Stack space is limited. On Linux, it's typically only about 8 megabytes by default. Layer after layer, it piles up. When it fills up completely, it's a stack overflow, and the program crashes immediately. Only after the stack frame is set up does the actual function logic get executed. Our add function just performs an addition. The parameters are already in the registers. So when the CPU executes add function, it reads the parameters from the registers, performs the addition, writes the result to RAX register, the designated return value register, and finally executes ret instruction. And what does ret do? It does exactly the opposite of call. It pops the return address from the top of the stack and jumps back to it. See, it's a perfect loop. Call pushes the return address. Ret pops the return address. This is the underlying mechanism that allows a function to leave and come back. At this point, many people might say, that's just a few instructions. How much performance cost can there be? A function call is indeed very lightweight, much lighter than a system call. But it still has a cost, especially in small functions called frequently, where this cost gets amplified. First, the cost of branch misprediction. The CPU works on a pipeline. It speculatively guesses where you'll jump next. Instructions like call and ret are indirect branches. If the guess is wrong, the entire pipeline must be flushed, costing anywhere from a dozen to several dozen clock cycles. Second, worsened cache locality. The stack is a contiguous block of memory, but frequently creating and destroying stack frames causes the CPU cache to swap data in and out often, reducing the cache hit rate. Third, registers must be saved and restored. x86 to 64 divides registers into two types. Caller saved registers. The calling function must save them before the call if their values are needed later, and callee saved registers. The called function must push them onto the stack before use and restore them after. These are extra instructions all consuming time. Fourth, it hinders compiler optimizations. A function call acts as an optimization boundary. It's difficult for the compiler to perform aggressive optimizations across function boundaries, such as constant propagation, dead code elimination, or loop unrolling. An inline can eliminate all these costs. What inline does is simple and direct. It copies and pastes the function body directly to the place where it's called. No call, no ret, no stack frame setup, no jumps. It effectively turns a function call back into regular code. This is why inlining small, frequently called functions leads to a noticeable performance improvement. So far, we've been discussing the most ordinary functions, but in C++, functions aren't just one kind. Switch to another type, and the underlying complexity can double instantly. The first type is virtual function calls. Virtual function equals polymorphism equals the specific function to call is determined at runtime. Under the hood, it relies on the virtual table and the virtual pointer. The calling process becomes get the virtual pointer from the object, find the virtual table from the virtual pointer, get the function address from the virtual table, and finally, call that address. This adds 2 memory accesses and 1 indirect jump, making branch prediction even harder. So, virtual functions are slower than regular functions. It's a physical, hardware-level slowdown. The second type is function pointer calls. The compiler has no idea where the jump will go at compile time. Only at runtime is the destination known. This is a purely indirect jump, and the CPU can hardly predict it at all, leading to even worse performance. The third type is tail calls and tail recursion. If the very last action of a function is simply calling another function with no further operations, the compiler can perform an optimization, tail call optimization. It directly reuses the current stack frame for the next function without creating a new one and without pushing a return address. Recursion instantly becomes a loop, and it will never cause a stack overflow. This is the ultimate optimization technique for writing recursive algorithms. The fourth type is cross-thread calls. This is no longer just a function call. This is a full-blown operating system-level thread context switch. It requires saving all registers, switching page tables, switching stacks, and flushing caches. The cost can be thousands or even tens of thousands of times higher than an ordinary function call. Now, let's look back for a moment. A function call, in essence, is not really invoking a function. It's a complete miniature state switch. From the CPU's perspective, every function call is a tiny context switch. It's just that it happens within the same thread, making it very lightweight. Understanding it at this level means you truly comprehend functions. If you found this content helpful, don't forget to like and subscribe. See you in the next video.